Welcome to this lecture. This is the second lecture of week 6. In the previous lecture, we have focused on pointwise convergences of distribution functions. We have discussed multiple examples through which we understand that if the pointwise limit of a sequence of distribution functions exist, then the limit function need not be a distribution function. Now, we have also looked at the Helly's selection theorem, which suggests that if we start with any sequence of distribution functions, then I can extract a convergent subsequence in the sense that there is a limit function where the convergence happens only at the points of continuity of the limit function. However, Helly's selection theorem is still unable to conclude that the limit function is a distribution function. Now, what we are going to focus on is a type of convergences involving distribution functions, where we will assume that the limit function is a distribution function, but we will insist on the pointwise convergence happening only at the points of continuity of the limit distribution function. Note that if I have any distribution function, then it may have at most countably many jumps or at most countably many discontinuity points. So, what happens is that if I take up any arbitrary distribution function, then either it will have no jumps, or it may have finitely many jumps, or it may have countably infinite jumps. So, what we are asking is that except that those jump points where the discontinuities appear, we want to have the convergence happening. So, with this we are going to consider this new mode of convergence. So, let us continue the discussion using the lecture notes. So, we are considering these pointwise limits of distribution functions given on the real line, and we are going to consider the higher dimensional analogues of this in later lectures. So, as already discussed in the previous lecture, we are working with distribution functions which correspond to certain sequences of probability measures or correspond to random variables. So, motivated by this discussion, we are now going to make this definition that we are going to consider a notion of convergence of distribution functions on the real line called weak convergence. So, what do we have? We have a sequence of distribution functions f 1, f 2, f n and so on, and another distribution function f. We are going to say that the sequence f n converges weakly to the distribution function f if this pointwise limit holds, but only at the continuity points of the distribution function f. So, the limit distribution function, which is capital F, may have these jump points which we are going to exclude from our analysis, and everywhere else where the distribution function capital F is continuous, we are going to ask for this type of a pointwise convergence, and this is what we are going to call as the weak convergence of distribution functions, and this is going to be denoted by this symbol where this arrow symbol will be used. Now, what we are going to do? We are going to extend this notion of convergences from distribution functions to the case involving probability measures and random variables. Now, we are going to consider probability measures which are defined on the real line together with the Borel sigma field, meaning these are Borel probability measures. For notational convenience, we are going to call them as probability measures on the real line. So, it will be understood that we are working with Borel probability measures. Now, here we extend that notion of convergence to sequences of probability measures on the real line. We are going to again call it as weak convergence. So, what is the setting? So, we are going to consider this sequence of probability measures mu 1, mu 2 and so on, and another probability measure mu, and we would like to talk about the convergence of the sequence mu n to mu. But now, first look at the corresponding distribution functions given by these notations f, f 1, f 2 and so on, and we are going to say that mu n will converge weakly if the corresponding distribution functions converge weakly, and we are going to adopt the same notational terminology or notational scheme that we are going to use this notation to denote the weak convergence of probability measures. So, again we are simply extending the notion that we discussed for distribution functions, and through that convergence we are going to define this convergence of probability measures called weak convergence. But again we are going to extend the same notion to the case of random variables. To be clear, let us look at this situation that I have two random variables, but possibly defined on different probability spaces. So, if x 1 is defined on omega 1 f 1 p 1 and x 2 is defined on omega 2 f 2 p 2, then the corresponding probability laws or the probability distributions are given by probability measures on the real line, and these are exactly the p 1 compose x 1 inverse and p 2 compose x 2 inverse. Now, we are going to extend these ideas of convergences to random variables through the corresponding convergences of the probability laws. So, let us look at this concept of convergence. So, here what we are considering now is this sequence of random variables, and we are going to consider a limit random variable x in this sense that first of all they are possibly defined on different probability spaces, that x is defined on omega f p, x 1 is defined on omega 1 f 1 p 1, x 2 is defined on omega 2 f 2 p 2 and so on. So, now we are going to look at the corresponding probability laws given by these, which are p compose x inverse, p 1 compose x 1 inverse and so on, and the corresponding distribution functions will be given by this. So, now what we are going to say is that x n converges weakly to the random variable x if the corresponding distribution functions converge weakly, or equivalently the corresponding probability laws converge weakly. So, we are simply extending the notion of convergences that we saw for distribution functions to probability measures as well as random variables. So, when you are considering a sequence of random variables, where the random variables may be possibly defined on different probability spaces, we can still consider this notion of convergence, that this notion of convergence is through the corresponding distribution functions or through the corresponding probability laws. This notion will be again called the weak convergence of these random variables. But now, specifically for this type of convergences involving random variables, sometimes we also use certain equivalent terminology. So, let us see those. So, we are going to call the weak convergence also as convergence in law or convergence in distribution. So, in this case the notion that we are discussing is the convergence of the sequence of random variables x n to the random variable x in law or in distribution or in the weak convergence sense. All right. So, with this background, let us see certain examples so that we understand this concept better. So, to do this, we just go back to our earlier example which we discussed in the previous lecture, that let us say x n is a sequence of random variables, and for each n the x n is actually degenerate at 1 over n. Then what we saw was that the pointwise limit of the distribution functions exist and it can be explicitly computed in this case. But now consider another random variable x which is degenerate at 0, and then here also the explicitly the distribution function is known. Now, for this random variable capital X which is degenerate at 0, the distribution function will have exactly one jump happening at the origin, and therefore, that is the only point of discontinuity of the distribution function f x. Now, if we exclude that from consideration, so for all non-zero small x, what we observe is that f x is exactly equal to the pointwise limit of the distribution functions that we considered earlier, where we are considering the sequence of distribution functions corresponding to the random variables x n, x n's being degenerate at 1 over n. So, therefore, for all non-zero x, what we end up having is that the pointwise limit holds, and therefore, we conclude that the degenerate random variables x n as n goes to infinity converge weakly to the degenerate random variable at 0, and this is also, as we have explained, the convergence in law as well as convergence in distribution. So, all these are equivalent terminologies when we are considering convergence of random variables in this sense. Now, here we can also restate the same result in terms of the corresponding probability measures. So, note that the law of these random variables that we are considering are given by the Dirac measures, which is the Dirac measure supported at 1 over n. So, for each natural number n, it is the Dirac measure supported at 1 over n, and what we are actually concluding here is that the Dirac measure at 1 over n converges in the sense of weak convergence to the Dirac measure at 0. So, with this we have essentially seen one explicit example of weak convergence in terms of the corresponding distribution functions, also in terms of the random variables and also in terms of probability measures. However, one important comment we would like to make about this fourth mode of convergence that we are considering. So, recall that earlier we had considered three modes of convergence of random variables, namely first was convergence almost surely, then convergence in LP and convergence in probability. All these three modes were for sequences of random variables defined on the same probability space. However, we are now considering a new mode of convergence where we do not require the same probability space and they can be defined on different probability spaces. So, the earlier three modes of convergence require that as part of their definition that the random variables must be defined on the same probability spaces. However, this new mode of convergence, the fourth type, the weak convergence, is not going to require that restriction. So, this is pretty relaxed mode of convergence, which we are going to compare with the known modes of convergence that we had discussed earlier later on. So, we are going to make this comparison with these previous three modes later on. All right. But now, we can reformulate the notion of weak convergences in other formulations. So, what we do is that we first recall a very basic fact that if we take a bounded and measurable function defined on the real line. So, this is a bounded Borel measurable function f. Then if I take any probability measure on the real line, let us denote it by mu, then for such a bounded Borel measurable function f and such a probability measure mu, this integration is always defined. And this extends to the fact that if I now consider a random variable defined on some probability space omega f p, then applying this bounded measurable function f, we end up with bounded random variable, and since we are having this bounded random variable y, which is the f composition with x, this will have all moments. Now, since it is having all moments, in particular the expected value of y also exists. This is just an extension of the previous idea that the integrals for bounded measurable functions always exist, where the integration is being considered with respect to probability measures. So, here what we are now considering is to going back to the definition of the expected value of y, which is nothing but the integration of y with respect to the underlying probability measure, and the integration is over omega. Now, note that since y is nothing but f composition with x, we can also think of it as expected value of f of x, and that is again in terms of the integration notation, the integration of f of x with the underlying probability measure on omega. However, here we can do the change of variables and we end up with this new measure, which is the law of the random variable x, and that is a probability measure on the real line. This integration is over the real line and we are integrating the bounded measurable function f with respect to the law of the random variable. So, here again we are going back to this previous fact that this integration always exists, because the function f is assumed to be bounded and measurable. And this identification of accepted value of f of x actually leads us to an interesting equivalent formulation of weak convergence, and this result is part of other general results called the Heilly-Bray theorems or the Portmanteau lemma or Portmanteau theorem. So, here we are going to consider a equivalent formulation of weak convergence, and note that the forward direction of the convergence is actually part of the Heilly-Bray theorem, whereas the equivalence, the whole equivalence, in particular the converse statement, is actually part of the Portmanteau theorem or the Portmanteau lemma. So, let us see this reformulation of the weak convergence that we are considering. So, we are going to state this result in two forms, one for the case of random variables and one for the case of probability measures. So, let us look at this sequence of random variables as considered earlier in definition 3. So, what we had considered earlier in definition 3 is that all these random variables are defined on possibly different probability spaces, and we want to consider the convergence of x n in the weak convergence sense to the random variable x. So, now the theorem says that this weak convergence is equivalent to this following fact, that if we consider all bounded and continuous functions on the real line, then the corresponding expectations which we are considering now, the expectations of f of x n, that will converge to expected value of f of x. So, now note here that we have improved the restriction on the functions f from measurables to continuous functions. So, that is the additional restriction that we are imposing here, because continuous functions are always measurable in this setting. So, now what we are suggesting is that for all bounded and continuous functions f on the real line, look at these expected values, and if these expected values converge to the corresponding quantity, and if this happens for all such functions f, then it is equivalent to the weak convergence of the sequence of random variables to the random variable x. And this is going to give us this alternative formulation or a equivalent formulation of the weak convergence of random variables. And this same statement can be restated for probability measures again. So, let us see the version for probability measures. So, now we are considering a sequence of probability measures on the real line. So, here what we are asking is that the sequence of probability measures converge weakly to this probability measure mu. This statement involving integrations with respect to now bounded and continuous functions. So, here we are considering bounded and continuous functions f, and we are going to require the integrations of the function f with respect to the probability measure mu n converge to integration of f with respect to the limit measure mu, and this limit should hold as n goes to infinity for all bounded and continuous functions f. So, if this limit holds for all bounded and continuous f, this is equivalent to the convergence of the probability measures mu n weakly to the probability measure mu. So, this is a very important reformulation that is going to give us another way of observing the weak convergence. Now, what we are going to do is to focus on the convergence of probability measures in this sense. Recall that what we have discussed so far is that first we have discussed the convergence of distribution functions, but then through that we have defined the same notion of convergences for sequences of probability measures on the real line and for random variables. Now, note that we have understood that we can essentially go back between one and the other, because it is always at the end of the day the corresponding sequence of distribution functions converging weakly to the corresponding limit distribution function. So, therefore, all we are going to focus on now is one fixed notion of convergence now for the probability measures first. So, let us start with a sequence of probability measures on the real line and discuss equivalent conditions for this, and as we understand we can always go back and reformulate if required through the corresponding notion of weak convergence for random variables. So, first we are going to see these equivalent notion or equivalent conditions for weak convergence of probability measures, and to do this we have a list of equivalent conditions. So, first of all we have already discussed this equivalent condition that we are considering the integration of bounded and continuous functions, and this result is actually part of a more general result, and that list of equivalent conditions is given here. So, what we do, this is the setting, we are going to consider a sequence of probability measures as considered earlier again on the real line with the Borel sigma field, and you are going to consider a limit probability measure which is denoted by mu. Then let us first write down the definition as the first condition, which is the notion of convergence that we are considering. So, here our definition is through the pointwise convergence of the corresponding distribution functions, but only at the continuity point small x of the limit distribution function f. So, here these distribution functions are corresponding to the given sequence of probability measures, but now we are going to look at all these alternative equivalent formulations. So, this second condition states that all we want is that kind of a convergence again, but only happening on a set D which happens to be a dense set in the real line, meaning this set D is supposed to be something such that the closure of D is the whole of the real line. So, for all points in this dense set, this pointwise convergence should hold, and if this holds, then this is a equivalent condition for the weak convergence of these probability measures. Now, we already have discussed as part of the theorem 2 earlier that this is a equivalent notion of convergence, that for all bounded and continuous functions on the real line, this limit should hold. The limits are involving this integration of the function f with respect to these probability measures. But now, we are also saying that this same kind of a condition can be imposed for restricted classes of functions. So, again if the same limit holds for all bounded and Lipschitz continuous functions on the real line, then this is also equivalent to the notion of weak convergence. Again we can consider a similar notion of convergence for only bounded and uniformly continuous functions. So, here if the same limit of integrations hold for all bounded and uniformly continuous functions, then we are claiming that this is equivalent to the weak convergence of the corresponding probability measures. And finally, we can also go to a more general class of functions where the functions are bounded and measurable. So, such functions on the real line, but with the additional condition they are continuous mu almost everywhere, meaning that except a set of measure 0 under the limit measure mu, except that set of measure 0, everywhere else the function should be continuous. So, that is the type of functions we are considering here, which are bounded and measurable and continuous in this sense. If we can ensure that the corresponding limit of integrations hold, then this is also equivalent to the notion of weak convergence of the probability measures. Now, here we look at another class of functions. So, we are asking for bounded and lower semi continuous functions on the real line, and for this if this limit inferior of the integrations is greater or equals to the integration of f with respect to the limit probability measure, then this condition is also equivalent to the weak convergence of probability measures. And a similar condition for bounded and upper semi continuous is given in terms of limit superiors and with respect to the other sided inequalities. We are going to discuss the proofs of these statements and discuss these concepts of lower semi continuities in a later lecture. Another equivalent condition to weak convergence is this: it is through measures of certain type of sets. So, if you only consider open sets G in the real line, then all you need to verify that the limit inferior of mu n sub G is greater or equals to mu of G. And similarly, you can also consider closed sets in the real line, and you ask for the opposite type of an inequality to hold for the limit superiors, and you want this condition to hold, and these are all equivalent to weak convergence of the probability measures mu n to the probability measure mu. And finally, we can also restate these in terms of more general sets, not necessarily opens or closed sets, but we are asking for this limit to hold, but only for mu continuity sets capital A. So, here by mu continuity sets we mean that this should be first of all a Borel subset of the real line, and we are only considering those sets such that the boundary of A, where this delta A denotes the boundary of A has the measure 0 under the limit probability measure. So, if such a set is available, we are going to call it a mu continuity set, and for such mu continuity sets we want this limit to hold. So, this condition is again in terms of sets and measures of those. And finally, we can also come back to our more familiar intervals and formulate the conditions in terms of that. So, let us look at all left open right closed intervals and ask for this limit to hold, but when the boundary has measure 0. So, here note that if we are considering all these left open right closed intervals, then the boundary is exactly given by these 2 point sets, and therefore, if this boundary has measure 0, then we are also going to end up claiming that this is equivalent to weak convergence. We can also restate it in terms of these half infinite intervals, that it is minus infinity to closed x, and this is for only those points small x such that the measure of this singleton set is 0. And note that this is exactly the same condition as f n of x, which is the corresponding distribution functions converging to f of x, where f of x is continuous. So, here the continuity condition is exactly this, that the measure of the singleton set small x, that is 0. So, this is exactly equivalent to the definition that we have stated earlier, but now it is in the form of measures of these intervals. And final condition is in terms of the corresponding characteristic functions. So, if the corresponding characteristic functions converge pointwise, now here note that we are asking for pointwise convergence for all points. Recall that the characteristic function exists for all points on the real line, and we are asking for the pointwise convergence throughout the real line. We are no more excluding any points, and if this convergence happens pointwise, then we are going to claim that this is also equivalent to weak convergence of the probability measures mu n to mu. Now, this list of equivalent conditions that we have discussed, we are going to see the proofs of these in subsequent lectures, but we are going to look at these conditions and get better ideas about the different types of ways we can look at the weak convergence of random variables as well as probability measures. But here you note that the equivalence that we considered in 1 and 14, meaning the 14 was through the convergence of the characteristic functions. So, this is actually part of something called the Levy's continuity theorem. And moreover, earlier we have also considered the equivalent conditions to 1 through these conditions involving integrations of certain classes of functions and also involving measures of certain types of sets, open sets, closed sets and mu continuity sets. So, all these types of conditions, the equivalence of that is actually part of the Portmanteau lemma or the Portmanteau theorem. So, we have stated it together, so that we have a good idea about all these different equivalent conditions instead of stating them separately. Now, one final important comment that we are looking at is this. So, suppose we are considering this sequence of random variables, each of which may be defined on different probability spaces. So, in order to check the corresponding random variables, what we understand is that we have to establish one of these equivalent conditions to the convergence in law for these sequence of probability measures, right. So, this is the weak convergence of the corresponding laws. So, now all we have to do to ensure the sequence of random variables converge weakly or in law or in distribution is to ensure one of the equivalent conditions ensuring the weak convergence of the corresponding probability laws. And therefore, this is going to give us multiple different ways to check whether some sequence of random variables are converging in the sense of convergence in law or convergence in distribution or in the sense of weak convergence. But typically we will focus on these three specific setting when we are focusing on random variables. Either we will discuss it through the corresponding distribution functions or through this type of expectations for bounded and continuous functions or through the pointwise convergence of the corresponding characteristic functions. So, whenever we are discussing about the corresponding distribution functions or the corresponding characteristic functions or the corresponding type of integrations, in these three specific situations we are going to get these type of convergences of random variables. So, we have multiple different ways we are going to attack and check whether a sequence of random variables converge in this sense or not. So, just to recall, we have defined a fourth type of convergence of random variables, which does not require the random variables to be defined on the same probability spaces. And here the notion of convergence is essentially through the convergence of the corresponding distribution functions, but the convergence asks pointwise convergence should hold only at the points of continuity of the limit distribution function. So, in subsequent lectures we are going to see the proofs of the equivalent statements that we have stated in this lecture, and we are also going to discuss further properties of weak convergence. We stop here. Thank you.